Okay. Hello, everyone. Welcome to this week's Rubin Science Assembly. We have a special guest speaker who's going to tell us about a research project done using the Data Preview 0 dataset and the RSP. Before we get to that, I have a few announcements, then we'll get to KV's talk, and we'll have plenty of time for Q&A. So definitely store up those questions. Okay, a couple of announcements. One, if you are interested and haven't yet registered for the Rubin Community Workshop, that is coming up at the end of July in Tucson. It is fully hybrid, but the in-person component of it has a limit of 250 attendees, which I think is, filling up fairly quickly. So if you're interested, do register. And there are links here. Before I forget, I will share the link to the slides. Ta-da. Okay. So links are in the slides if you are interested. I put a link here to a press release from a little while back about installing the camera. Also note that if you were planning to submit input to this call for community filters for Antares, that is due tomorrow. So there's a link here for more information if you want to submit something for that. Upcoming science assemblies next week will be a drop-in discussion Q&A session where some of us will be available for any questions or discussion items you might bring. And then the following week, we'll have a presentation by Claire Higgs from the Rubin EPO team about citizen science with the LSST. Where are you working? There we are. One other announcement you may have seen, but in case you haven't, it has been announced that the first look celebration of Rubin, the first public unveiling of Rubin imaging is scheduled for Monday, June 23rd. There are links here for more information. Again, the slides are shared in the chat. This includes an official press conference coming to you from Washington, D.C., and other associated events. And you can see here, this is a map that I took from the website. These are all of the venues that have signed up to host watch parties for this event. So you can go to this site and see if there's a watch party near you and go and join in person a group of people all watching this event in person. So do check that out. This is pretty impressive, the number of venues on this map. Sorry, not working. We would like to remind you that there is a Rubin Users Committee. Their purpose is to solicit feedback from the community, from you, about the data products and the science platform and your experience using all of these. And they then provide feedback and recommendations to the directorship of the project. So there's a lot more information here about what they do, but do reach out to them. They have this Google form that you can send them feedback. Do reach out to them if you have concerns or even positive feedback. They are always happy to hear from you. We also would like to remind you that the Link Frameworks team has office hours on most Thursdays at 10 a.m. Pacific, which is the hour directly after this hour. Link Frameworks is an organization that is building a lot of software and tools to help users take advantage of the massive data set that is coming from LSST. So if you want to know more, there are lots of links here on the slides, which I will reshare because I know more people have joined. And do drop in and chat with them if you are interested. Okay, I don't know why that transition happened, but just a few links. Again, you can see these on the slides. If you're new and you don't yet have a Science Platform account, there is a link for how to sign up for that. And of course, documentation for Data Preview 0, information looking ahead to Data Preview 1, which is coming very soon, where there will be real on-sky data from the commissioning camera released and available for you. And a couple of more links to the community forum and the website. But I think for now, oops, that is all the announcements I had. I was going to pause for questions, but I don't think we need to. I think I will stop sharing here, and we will move on to today's presentation, which comes to you from KB Tsiane, who is a grad student at University of Michigan and is here to tell us about, I think, a really cool project using the Data Preview 0 data to estimate our sensitivity to tiny dwarf galaxies and star clusters around the Milky Way. So you are free to take it away, KB.
Awesome. Thank you very much. Hello, everyone. Let me share my screen. All right. Can everyone see that?
Looks good.
Fantastic. All right. Good morning / good afternoon, everyone. I am Kabelo Tsiane, or KB, and today I'll be presenting on our project, which, as Jeff introduced, is on predictions for the detectability of Milky Way satellite galaxies and outer halo star clusters. All right, so why did we do this? Well, observational and theoretical arguments for the current census of the Milky Way satellite population suggest that the census is very much incomplete. And this is best captured, I think, in what is known as the satellite luminosity function, which I plot over here on the right. So this just reports the cumulative number of satellites below a given brightness threshold, magnitude threshold. And so what we can see from this plot here, based on a fiducial all-sky population of the fiducial all-sky model of the Milky Way's satellite population, that is the blue band here, we can see that theoretically we have good support and observations are pretty much complete at this brighter end of the distribution of the luminosity function that is past a magnitude of about -8. But as you go to these fainter and fainter magnitudes, we start to see a discrepancy between the model prediction and what we actually observe in the distribution of the satellite population. So in times long past, I think at the time when I started this, maybe a few years before I started this project, this was known as the missing satellite problem. But after a bunch of completeness corrections are applied to our current uh, uh, population, we actually find that current observations are pretty much in line with what we expect from a lambda CDM view of the universe with hierarchical structure formation giving rise to these sudden amounts of these small scale structures and dwarf galaxies showing up. Either way, this is still something worth probing. This ultra-faint dwarf regime, overplotted as well as all the known satellites and those that fall within the LSST footprint. So really the thing that we want to focus on here is the ultra-faint dwarf detections. Ultra-faint being those below a magnitude of like -5, very compact as well, with sizes bounded above by about like 10 kiloparsecs, I believe. Or yeah, something of that order. So ultra-faint dwarfs, they're really cool. Outside of having a complete census, what else can we do with these systems? Well, they allow us to probe things like galaxy formation. So these are very old mesopore systems, and for particularly distant ones, they are free from the tidal influence of the Milky Way's disk, which gives us a really cool, a really great laboratory for actually investigating, these limits of galaxy formation and what these processes look like in these systems. We can also look at the local redshift of reionization based on these satellite populations, which I'll get into a bit, as well as also probing the microphysical properties of dark matter as well. So a bunch of really cool stuff we can do just with these population statistics. And so the goal of our work here is to predict the detectability of these systems, as well as outer halo star clusters with the Vera Rubin Observatory using simulated satellite systems. So the reason also why we include these outer halo star clusters is because at these sizes and luminosities, there's very little that our search algorithm does to differentiate between the two. There's no distinction that can be drawn between them. Okay. And so, like I said, what we can do is we can look at the reionization, the local reionization redshift based off of these statistics. So after reionization, we know that we have a UV background that permeates throughout the intergalactic medium. This heats up these particles after the reionization, and this suppresses gas accretion below some time-dependent mass scale. And so that reheating allows these particles to jump out of these shallow wells that are these shallow potential wells for these very small subhalos in the ultra-faint dwarf regime. The faint end of our luminosity function is what is going to probe this effect. The bright end is not so much sensitive to this. That'll be more sensitive to like your galactic outflows and other more significant feedback processes. But what we can see here from the team, from Kravtsov and Manuel from 2022, is that uh, there is separation between different models for the reionization redshift as you go to this ultra faint regime right here. I should explain. So these are also the luminosity functions for DES, Pan-STARRS 1, and SDSS plus classical. I forget what this classical, how they define this. And then overplotted are the actual observed dwarfs within each of these surveys, right? So if you look at the reionization redshift, you can see that at the faint end, there's separation in the different models, and there's a trend as you go from higher to lower redshifts, right? Because again, if you have a higher redshift of reionization, you would get more of that suppression, that gas accretion suppression effect that is gonna suppress your Milky Way, your satellite statistics at this faint end. Another thing that we can do is put constraints on our dark matter properties. So plotted here, we have the transfer function here defined as just the ratio of the power spectrum of some non-dark matter scenario, a non-standard dark matter universe. The ratio of that to just our standard cold dark matter universe. And so what we can see is that at small scales, these non-standard dark matter interactions or non-standard dark matter models will suppress the formation of these small scale structures. So here we have warm dark matter, we have interacting dark matter, and we have fuzzy dark matter. And this gray dotted line at the top is just the power spectrum for our standard cold dark matter. And so the reason for for the suppression of the small scale structure in the different dark matter models, it varies. I won't get into it too much, but from these plots here, authors here were able to also rule out. So what they're actually plotting here are ruled out dark matter models. And from that, you can put constraints on these dark matter models just from these population statistics. So for example, here, in the warm dark matter case, at the time of this paper, they were able to put a lower limit on the warm dark matter mass of about 6.5 keV. I think that has risen as of, I believe, last year to about 10 keV. They're able to constrain the dark matter proton scattering cross section as well as the fuzzy dark matter particle mass. All right, so then the middle panel here shows us the suppression factor that you would attach to the subhalo mass function for a non-standard dark matter relative to CDM. And again, we can see that at these lower mass scales, this suppression effect is a lot stronger for the non-standard dark matter. And finally, on the right, we have another luminosity function. Same thing, you have the different dark matter models, the model uncertainties for the warm dark matter scenario, and we can see that there is, at this level, there's just enough evidence against this at the faint end of the luminosity function that rules out these models. So just to summarize again, this slide, we have non-CDM physics, non-cold dark matter physics that is going to suppress our linear matter power spectrum on small scales. That is this plot on the left in this region, which leads to an underabundance of subhalos, which is this middle panel here, and therefore faint Milky Way satellites, which is this far panel here. So there is a lot of cool stuff that we can do with these satellite population statistics outside of just knowing where everything is in the sky and our local environment, right? Okay, so the data set that we use is LSST's DC2 data. That comprises our background objects, our field objects. However, for the actual simulated satellites, we generate our own catalogs. The procedure for that is as follows. So we take the key photometric properties of the DC2 catalog. That would be our photometric uncertainty, detection probability, and star galaxy classification efficiency. And we use those to generate consistent catalog level simulations of the satellite galaxies so that we can feed them into DC2, merge them with the DC2 field in a reasonable and comparable way. So first, let me talk about the plot on the right. So we have a plot of the efficiency versus R-band magnitude and the difference between the true R-band magnitude of an object minus the R-band magnitude of the magnitude limit map in the R-band at that location in the sky. So on the left here, those magnitude limit maps for the G and R-band for 5 signals noise point source. Signals to noise of 5 point source depth. Right, so to quantify first, let me talk about the classification. So to quantify that star galaxy classification efficiency, we just select a small three square degree region of the DC2 field of well-measured objects with truth matches, and we compare those with the measured classification. Here, the measured classification that we use is just the extendedness parameter in the DP0 tables. This extendedness parameter is just a Boolean classification where something with an extendedness of 0 is a star and something with an extendedness of 1 is a galaxy. Right, so we do that to characterize the classification efficiency as a function of R. And then, in order to characterize the detection efficiency of these stellar objects, we just track all the stars in the region with truth matches, and we bin these populations in true R-band magnitude. So a key feature from this plot that we use throughout the analysis is this very steep drop-off that we see in the detection and classification efficiency around an R-band magnitude of 26 right here. Okay. So then for the photometric error model, here I've plotted the uncertainty in the R-band magnitude as a function of R-band magnitude and that delta R parameter I described before. We compute the median of the logarithm of this magnitude uncertainty as a function of the difference between the true input magnitude at the true input magnitude and value of the magnitude limit map at the location of that object. And so this model for the expected magnitude uncertainty as a function of magnitude and survey magnitude limit is applied to the simulated satellite member stars in order to generate realistic photometric scatter in magnitude and color. Okay. Okay, and so for our simulated satellites, so the table on the right just shows the parameter ranges for the simulated satellites that we use. We wanted a nice broad range of satellite parameters so that there's no bias in our search algorithm. So that we don't introduce any unwanted bias in the algorithm. So we generate 100,000 such satellites at the catalog level as collections of individually resolved stars. We then use a probabilistic model to model the spatial distribution and the flux distribution of the stars in each of these satellite in each of the satellites. So for spatial distributions, the stars are just sample of the stars. We just sample from a simple Plummer profile. Okay, then we use the simulated elasticity band passes, which I have over here, that were used for DC2, and we integrated into the Padova CMD interface to generate photometry that is consistent with DC2. Our stellar initial masses are then drawn from a Chabrier initial mass function. From there, we use that to assign the current absolute magnitudes of those satellites from Amerigo isochrone. All right, so that is the data. Now, what do we do with this data? So for each satellite in this DC2 region, what we do is we will, broadly speaking, for each satellite, we will inject the satellite at the location, at its true location and true distance from the Milky Way, and run our search algorithm on it. So first of all, we will query the Rubin table access protocol service for the DC2 objects that are within 2 degrees of that satellite. So that's just this plot here in the lower left. After we query that data, we take our simulated satellite and we inject it at the center of that data. This part on the right here, you can't really see it, but it is there. And this is a very detectable satellite for our search algorithm. So, yep, but this is what it looks like. So then we inject the satellite there, and we have a new merged data frame. From that merged data frame, we just select all objects with a magnitude error in the G and R band of less than zero point 0.2, which corresponds to a signal to noise greater than 5, greater than or equal to 5. Okay, and then of those objects, we again apply another cut in the G and R band magnitude at magnitudes of 26. Again, this is due to that steep drop in stellar detection and classification efficiency that I had shown in the plot, the previous plot. Okay.
KB, can I butt in for a sec? Sorry. Um,
Mhm.
it seems like your pointer is like misaligned with the slides on the screen. Like when you're pointing at things, I think it's not showing up to us as where you're
Oh,
trying to point. So I wonder if you like unshare and then reshare screen, if it'll fix itself.
yeah, let me try. Sorry about that.
I've never seen that before. It's totally weird.
Okay. So is this hovering around the center panel right now?
Is now perfect.
Okay. Okay.
That was weird. So okay, sorry to butt in.
That is no worries at all. No worries at all. Okay. Cool. Okay, so this is the injection and selection and kind of like rejection part of what we do with the DC2 data plus the simulated satellite data and just how we clean it up, right? Okay, so we have the data prepared for the satellite. Now we are going to run our search algorithm on it. So the algorithm is known as simple because it's pretty simple the way that this algorithm works. It's very nice. So simple works by first it creates an annulus around some region of interest, and it's going to apply an isochrone filter in color magnitude space. And so I show that here. This red, the isochrone is right here. Highlighted in red, these red circles, these are the satellite's member stars. The red dot dash line is also just simply again, that G and R band magnitude cutoff, less than 26 that I spoke about earlier. So at this stage, there's two panels for reasons I'll motivate in a moment, but an important thing to kind of take away from these CMDs is kind of in the measure classification scenario, that is with using that extendedness parameter, at these fainter magnitudes, you have almost 2 orders of magnitudes more objects compared to, sorry, 2 orders of magnitudes more objects as compared to the perfect, when we use truth information on the objects. That is truth information on DC2 and our simulated satellites, right? So we'll get into why we do this separation in a bit, but for now, this is what simple does. It looks up. Okay, so then simple is then going to identify local density peaks by iteratively raising density thresholds until we have fewer than 10 disconnected density peaks within the region that we feed simple, right? With this filtered field, it's just going to smooth the filtered field with some Gaussian kernel. It's then going to just determine the angular size of some circular aperture that will maximize the significance of the density peak with respect to the distribution of the distribution of background DC2 stars. Right? And then after that, simple is just gonna come with an expected number of stars calculated at that peak. And the way that works is that simple is gonna First, it's going to compute the characteristic local density in that region. And it does this by counting stars in an annulus in a 0.3 to 0.5 degree, in an annulus from 0.3 to 0.5 degrees. It then has an inner aperture that is going to fix, that's going to range from 0.01 to 0.3 degrees as well. This characteristic local density is then combined with that aperture size to predict the expected number of stars in that field rather. After you get this model predicted number, then Simple goes in and actually observes the number of stars that it can see, right? And the main output from this is going to be the Poisson detection significance, which ranges from 0 to 37.5. And that upper limit on the detection significance is it's a statistical reasoning for why it's that very somewhat specific number, which I could try and motivate a bit well if people are curious. Okay, from here, yes, then for our detection criteria, we just simply classify an object, a system, as detected if that significance of detection is greater than 5.5. And this is it's a historical, kind of a historical choice, this value of 5.5. It's based on a previous, somewhat similar analysis that was done on DS and pan-stars, where the authors found that if you drop the significance below 5.5, there's a very large increase in the number of required follow-up systems, follow-up analyses required on these candidate systems that they would find, which was a bit cumbersome. You know, there was a lot of false positive detections that would come with this. And also at this level of 5.5, there is authors found that on real data, it is pretty clear to tell whether you're looking at some just survey artifact or if you're looking at, you know, a genuine stellar system that we're interested in. All right, so again, I'm gonna just highlight this, you know, just the sheer number of objects here as compared to the perfect star galaxy separation case. And I'm gonna try and motivate why this is important, because in our first round of results, what we found is that the measured classification scenario had performance that was pretty comparable to the ideal scenario, especially at like further distances, which, you know, it doesn't happen really in real life. We're like, okay, is it really going to be this amazing? Is it really going to be this great? Well, we had to find out what was wrong. So we had to figure out where all these objects, again, 2 orders of magnitude more objects, where all these objects are coming from, what could they be, and if and how that would be skewing our results. We needed to characterize kind of the background field here, the background DC2 field, right? Oh, sorry. I should also mention an important feature. So another thing that makes simple so simple is that in these isochrones, what I've shown you here is that even though I've highlighted the member stars, Simple is not able to separate out these member stars completely from the background DC2 field, right? Some of these background objects are going to leak in to what Simple sees, and it will affect how it reports the significance of that detection. Hence the skewed results that we found first time around. So the next step here is then to just try and characterize the background field and see what is going on there. So if we interpret our detection significance as kind of a Gaussian p-value to yield the chance probability of some false positive detection, this relies on the assumption that we have a uniform background, and that this uniform background model is correct for our data. You know, DC2 LSST is going to be operating, or at least the DC2 field, sorry, is at high galactic latitudes. And so this was an assumption that we started with. We're like, okay, there shouldn't be too much of an effect here if you make this assumption. But again, our results suggested maybe not. So we run a pretty simple background test. We query the DC2, we query Rubin tap again for about 1,000 of these regions in the DC2 field for each region. And this time around, we do not insert our simulated satellite into the region. We just run simple on that region. We store that significance of detection. We then shuffle the objects within the region, and then we're going to run simple again. We're going to store that significance again. And then we just take the difference of the old and new significance, and that's the delta sig value that we have here. And so in a scenario where if we were to actually have a uniform background, we would expect that, you know, this should be roughly centered on a delta sig of 0, right? Simple should not be able to pick up on any structures if we have a truly uniform field. And that is the case mostly in the idealized classification scenario. We can see that it is centered on 0. That's this red histogram here. We can see that it is centered on 0. However, there is still a false positive detection rate of about 2%, which isn't too much of a deal breaker. However, when we use when we do it on the measure classification scenario, you can see that there is a huge tail, a huge skew here towards more positive values of delta sig, which suggests that before the shuffling, we're getting higher values of highest, we're getting more significant detections before we do that randomized shuffle, which suggests that simple is actually picking up on some structures in the DC2 field that could be what is skewing those results. Could be what was skewing the results to be so good, right? And so what we actually found is that this measured configuration returns a 22% false positive detection rate, which is it's pretty high. And it could waste a lot of time for follow-up, when you want to do your follow-up analyses and whatnot. So to correct for this very high false positive detection rate, we simply increase the detection of significance in this measured scenario, and that drops down our false positive rate to about 2% as well. So this makes it makes it much better, much easier, and much fairer to compare this measured scenario, or let's say the real scenario with this idealized perfect scenario, right? So this contamination, it's an effect that could be mitigated if you had a more advanced search algorithm and not just simple. For example, if you had an algorithm that incorporates information about the expected initial mass function of the stellar systems you're looking for, that could help it could help a lot with this type of contamination. Such algorithm does exist, but that is not the focus of this work here. Okay. All right. So at the end of this song and dance, what do we get? So what we want to, again, just to remind us of the picture, what we're really going for here is that we want to be able to characterize the Milky Way satellite population. We want some luminosity function that tells us kind of the distribution of satellite properties within the Milky Way's neighborhood, right? So you need three ingredients to get to that luminosity function. Here's the first of those ingredients. The first is what is known as the observational selection function, which I plot on the right here. All that this does is that it reports the probability that a satellite will be detected as a function of its physical properties of heliocentric distance, absolute V-band magnitude, and half-light radius. Right? So we have this overplotted. I have this plotted on the right here. We split it into 6 different distance bins ranging from 8 kiloparsecs to 500 kiloparsecs down here. So increasing in distance, going from left to right and top down. Colored, the plots are colored by detection efficiency, which is just the ratio of detected within a particular bin, the number of detected satellites to the total number of satellites. Overplotted here are what are known as the 50% detection efficiency contours. These are very useful parameters. It's a very useful, quick analytical parameterization to, understand kind of the sensitivity of the survey that you're using, right? So for comparison's sake, I include the DES 50% detection efficiency contour just so we can see, just the real gains in sensitivity and like resolution that we can get, that we project that we will get from LSST operations at the end of a 10-year survey. So going from the outside going in, or from least sensitive to most sensitive, we first have the DES contour. Then have our the measured and corrected classification scenario. So that is with a comparable false positive detection rate to our perfect scenario. This is again what would be kind of the more real, what we would really expect to see as far as sensitivity. We then have the regular measured classification scenario, which is the red dot dash line. And then finally, we have the idealized scenario with perfect star galaxy classification efficiency. And so we can see at every single distance, LSST is more sensitive. We expect it to be a lot more sensitive than DES to these, these faint systems. And it also does highlight the importance of having good star galaxy classification efficiency. If you really want to push out into these regions of the parameter space, get into the really faint, the really distant, compact satellites, we need We need better and better star galaxy classification efficiency. Okay, so the 50% detection, this contour, it is again a useful, quick analytical approximation. But what we then go on to do is we train a gradient boosted decision tree classifier, which helps us to fully characterize now this OSF parameter space. And it is essentially the same, you do essentially get the same plot, it's just smoothed out a lot better, a lot more, rather. Okay. So this is the first ingredient to get in the luminosity function. The second ingredient that we need is predictions for the depth and coverage for 10 years of LSST operations. Right, so we estimate the coverage and depth of LSST's operations using the baseline version 4 OPSIM package. So this model just reflects our current understanding of system throughput and the observing strategy that the LSST wide-fast program will be deploying. I will note here that this version of the OPSIM package does represent a very significant update from the operations that we used to generate DC2. However, when we compared the maps, we actually find a comparable median depth in the GNR bands from those magnitude limit maps again. So this is it's still a fair comparison to feed this into the pipeline for generating that luminosity function. Okay, so with these maps, we also apply some masks. So first of all, we restrict it to regions that have signal to noise, a signal to noise equal to 5 point source depth in the GNR band magnitude, above that 26 magnitude threshold that I spoke about earlier. Again, reflecting the how we did the rest of the analysis. We also mask those regions in the sky that could make detections of these faint systems really, really complicated. So these are regions with like a lot of extinction due to a lot of it like interstellar dust, regions with really bright stars, regions with globular clusters and Magellanic clouds and their associated, yeah, and all that mess. And the result is that we have a footprint of an area of about 18,300 square degrees, which is down from the projected, I believe it's like 19,000, 28,000 square degrees of the full and proper survey. All right, so here's the map. And then the final ingredient that we need for the luminosity function is what is known as the galaxy halo connection model. All that this does is that it parameterizes the relationship between our satellites and the subhalo and its the dark matter subhalo's properties, as well as including effects due to baryonic physics on the subhalo population, such as tidal disruption, for example, from the Milky Way's disk. So we sampled posteriors from the Galaxy Halo model parameters that were derived from fitting data from DS and PanSTARRS-1 from a previous team as well. The way that they constrain that model is as follows. This is just a kind of a broad rundown, a broad rundown of what that process looked like. So first they resimulate Milky Way-like halos from a large cosmological volume. They then have some priors for these parameters, and then they paint satellite galaxies onto subhalos using those priors. You then apply the observational selection functions based on actual imaging data that they have, so from DS and PanSTARRS-1. From that, you can then calculate the likelihood of the observed satellite properties given the Galaxy Halo connection parameters. And then you just iterate, what they do is then just iterate on this process to constrain this model. And so here's just a quick rundown here, the posteriors and some of the parameters of that model. So we have the faint end power law slope, we have the scatter and the luminosity, we have the 50% occupation mass, we have the strength of subhalo disruption due to baryons in the Milky Way's disk and other effects and other feedback processes. We have the scatter in the galaxy occupation fraction. We also have the amplitude of the galaxy halo size relation, the scatter in that relation, as well as the power law index of that relation. Right. And great. So we have the three main ingredients. Everything is looking good. We're almost there. Now this is the plot again, the luminosity function that I showed you at the beginning with that fiducial all sky satellite population model. And all the known discovered satellites, confirmed Milky Way satellites. Again, we are focusing only on this faint, on the faint regime, with compact systems that LSST will detect within the virial radius of the Milky Way. That is within the 300 kiloparsec volume of the Milky Way as a function of his satellite luminosity. So after we combine all those ingredients and, after all this song and dance, we get the following. So with LSST, this is what our luminosity function, this is what we predict our luminosity function will look like at the end of the 10-year program. So again, the blue contour represents a fiducial all-sky satellite population model for the Milky Way, right? In gray, we have the LSST predictions. We include the median values, the mean values in each bin the median values of each bin is plotted here for the perfect scenario, the measured, and the measured and corrected scenario, right? And so what we predict is that LSST at the end of the 10 years will be able to detect 89 such satellite systems if we assume perfect star-galaxy separation. And this corresponds to 53 new discoveries. That is the absolute, that is the limit, the idealized scenario that we are projecting. In the measured scenario with all those false positives, this drops a bit to 83 such detections with 47 new discoveries. And if we apply the correction to account for the false positives, it drops even further to 67 such discoveries. To 67 such systems with 31 new discoveries. And so again, these statistics, they do really emphasize, again, the importance of having good star galaxy classification efficiency if you want to like really, constrain and like fill out the census of the Milky Way satellite population. This is, it's really important. And so from the fiducial all-sky population model, that model predicts that the Milky Way has some 220 satellite galaxies in the entire sky. These faint compact systems, right? Just to put that into context, that value compared to our predictions, this suggests that, LSST only covers 44% of the entire sky. And with perfect star galaxy separation, we'll find that LSST could be able to detect up to 90% of the Milky Way satellite galaxy population with all those cuts that we apply, which I think is it's pretty remarkable and really interesting. It'll be really interesting to see if this is the case and this is what turns out. I hope at the end of these 10 years, you all remember me and these predictions that I made. Hopefully they're right. If they're not, we'll see what changed. There'll be something interesting to say about that. Okay, so what else can we say about our new detections? So the physical properties of these new detections. Well, here I've plotted again, not again, but here I'm plotting just the brightnesses as functions of their sizes and the distances. These red filled circles are confirmed Milky Way dwarf galaxies. The open circles are candidate systems. And so the model is predicting that LSST will be able to detect fainter, more compact systems, that is like this region of the parameter space, as well as more distant systems. That's this region on this plot here of the parameter space, which is pretty cool, very useful for filling out the census, which is great. So again, being able to detect these more distant systems, like I said, this gives us a really good avenue for, probing the threshold of galaxy formation, because, we don't have to worry about the tidal influence of the Milky Way's disk anymore at these distances. Or rather, you don't have to worry as much. It's not as much of an effect. But again, probing these really faint compact systems, it fills out our luminosity function at that faint end, allowing us to probe that local redshift of reionization, probing the different dark matter, microphysical dark matter models and dark matter properties, which is, it's a great time to be alive. Be very fun to see how this goes and if it works out this way. But that is it. Yes, that is the end of my presentation. Thank you all for listening.
Thanks so much, KB. We do have time for questions, so if anyone has questions. There aren't a whole lot of us here, so you're free to just unmute and ask your question. I see Bob's hand.
Nice work, KB. You really dug into this.
Thank you.
I'm wondering more about some of the parameters for identifying the faint dwarfs. Like, I mean, background subtraction's got to be critical, and the amount of dust in the galaxy and between you and the galaxy. I mean, can you comment on some of that?
I mean, so given that DC2 is that would be an important feature for actual operations, but given that DC2 is so for our analysis, we do see what it looks like when we apply these corrections for like things like interstellar dust, like dereddening and stuff.
Right.
It didn't at these latitudes, it has like a very negligible effect. It's something like a 0.2% effect on our final results, actually. So at least here, that would not be too much of an issue, but in real observations, I imagine, yeah, it would be something we need to take care of.
I worry too about the background subtraction, just the algorithms that do that, where you might take a faint dwarf galaxy as just as background, and
Yeah.
that's got to be a big issue.
Definitely, especially so with simple, especially with how it like classifies things as not detected, even like those really faint systems, they could elude our detection here still. On top of that, we have the like just the pipelines on how we like do that background subtraction, how we pre-process that data. It could remove these really faint satellites from what we would actually like be able to find. Yeah. I can't think of like off the top of my head any way to like correct for that or counter that or try and mitigate that. Like we can't just say kind of give us all the raw data and let's hope let's hope Simple just does the best job ever. Yeah.
Yeah,
What was the
Jen,
question? Mhm.
Jen, you have a question?
Hey, Ray, this is really nice work. So just a couple quick questions for you. First, I saw the link to get Jeff's slides. Do you have a link to get your slides?
I don't, but I can put these on Google Slides and share that.
Okay. Thanks. I would absolutely appreciate that. So algorithmically, I'm very interested in this type of stuff. Are these things available? I don't know if we have the depth in any of the stuff that we available for the DP samples. Is this something we could actually try to see through the available data preview samples to see if we can do some of these detections of these satellites, or at least the star galaxy separations? Yeah, sorry to ask you that, but is that something that we can start to experiment with just to see how this actually plays out?
You mean like just on the DP0?
Exactly.
None of our semi satellites. That's a good question. I wouldn't know, unfortunately. Yeah, I wouldn't know. I don't know if DC2 does simulate these systems as well. Because I know it does the large scale structure and then it also has a simulation of the Milky Way's satellite population. Is that right? Not satellite population, but the Milky Way's halo. But as far as the satellite population, I don't know if.
Yeah, those aren't included in the simulations, unfortunately. So we have to wait for the real sky.
Yeah.
Do you guys know by chance, just thinking about commissioning then, I know we're pointing, but I'm thinking about the background within any of the commissioning fields. Do you know if then we could probably experiment with any of those? Sorry, I guess I'm kind of anxious and excited to get going on this type of stuff. Do you know if any of those might be sufficiently quote unquote, prime targets to try to, implement some of these algorithms? What do you think?
No, I wouldn't know. Sorry.
Okay. All right. Okay. Well, great. I'll just look forward to the slides, and then I'll just see if we'll just experiment and try to see what we can do. Thanks.
Sure, of course.
Hey,
Yeah,
KB.
and
I'm
go
sorry.
ahead, Bob.
KB, have you got plans for DP1?
I don't. At the moment, no, I don't. There's nothing in the immediate future with that we're going to be working with. No.
Oh, I was going to add in response to Jen's question, the data preview 2, which will be on sky commissioning data from Ellis's TCAM, will likely contain, I mean, it all kind of depends on how things shake out, but will likely contain, you know, hundreds of degrees of sky at least, you know, 2-year depth. So we will definitely by DP2 have a data set that is worth trying this all out on. DP1 is a very small area of sky. So yeah, so the commissioning data, I think, to answer your question, will be a really good test bed for like how well these techniques are going to work.
Yeah. Yeah. Could I ask a quick follow-up to that, Jeff?
Thanks for that.
At what year are we expecting to have, like, after how long do we expect to have like having a full sky observation like coverage? When do you think that would be?
I mean, the commissioning data will be, yeah, just I won't commit to a number because we don't know, but you know, a few hundred to 1,000 square degrees, and then definitely within the first year, the entire southern sky will be covered. So then that day, but yeah, actually within the first data release 1 will come from the first 6 months of data. So that should likely cover the entire southern sky. And so data release 1 will be early, oh my goodness, 2027.
Oh, okay. Okay, cool.
I was going to ask this plot. One of the striking things to me, I mean, it's really cool that we're going to find these things that have a total luminosity of like one bright star, essentially. But it's also kind of amazing to me the difference between the red curve and the predicted curve at like -7, which is a pretty bright dwarf galaxy. Like it looks like this predicts that we might find a few pretty darn bright dwarf
Oh.
galaxies at like -6, -7. And I guess it's surprising that we haven't found them yet. Do you have an idea? Are those like maybe more distant than we've been sensitive to with DES or other surveys, or?
That would be my bet, because this is the absolute magnitude. So the only reason I could imagine why we haven't seen it is just that it's just really faint because it's so far away.
Yeah.
Yeah.
Which is pretty cool. We'll find things way out at the edge of the halo.
Yeah.
Awesome. Okay. I pasted a link to KB's article on this work in the chat. It is on the archive, so if you want to know more, there's.
Oh, let me put these on Google Slides and share the link in chat as well.
Great, thanks. Any other questions anyone have? Well, thanks everybody for being here today, and thanks so much for a great talk, KB, and a great use of data preview 0, which it's good to see science papers coming out of the data previews. And yeah, I won't pressure you to get the slide link in real time, but we could share it on the. I'll post the recording of the talk on the community forum as a reply to the announcement post, and you could put the link to your slides there if that's cool with you.
Yep.
Okay. All right. Thanks everybody, and have a great rest of your Thursday.
That's great work, KB.
Thank you. Thanks, everyone.
Y'all take care.